So, hello all, welcome to lecture 35. So, today we will look at again continuation of what we have left off in the last class, and that is so we were looking at what are called microcanonical ensembles. We looked at eigen system, a two level system, a very simple nice two level system where there is only one macro state, whereas so there were 252 different microstates for our 10 spin system with a total energy of 0, right. So, in some magnetic field, of course, so that defines the energy of the spin, but the total energy of all the system should be 0, and that is achieved by having 5 spins up, 5 spins down, and that is sort of the microscopic picture of saying that the energy is 0, the magnetization is 0, but still you have spins, right. So, in the system that should either be up or down. So, these are the constraints. This is a simple model system that we have looked at, right. Now, if we have a 3 level system, for example, right. So, a 3 level system where I have epsilon, so this is epsilon naught, so let us just say this is minus epsilon equal to minus epsilon naught. Here I have epsilon equal to 0, here I have epsilon equal to epsilon naught, right. So, this is a 3 level system, and I have n equal to 10, again E equal to 0. So, if I have E equal to 0, that means so the number of particles, and so if I put n1 particles here and n2 particles here, n1 should be equal to n2, right. So, number of particles in epsilon equal to minus epsilon naught and epsilon equal to epsilon naught should be the same. Only then can E be equal to 0, right. Okay. So, instead of writing n1 and n2, I am just going to write this as n1, both of them as n1. Okay. And total number of particles is capital N. So, I will put minus 2 n1 here, right. But so I can keep changing the value of n1, right. So, for n equal to 10, n1 can be either 0, right. So, I can put all the 10 particles in epsilon equal to 0, and I have I satisfied both the constraints, right. So, n equal to 10, E equal to 0, right. So, I satisfy both the constraints by having so all the particles in state 2, which is epsilon equal to 0, or n1 equal to 1, or so I can have n1 equal to 5, right. So, when n1 equal to 5, all the particles, when n1 equal to 5, all particles are either are in epsilon equal to minus epsilon naught and epsilon equal to plus epsilon naught, and none of them are in epsilon equal to 0, right. And that is divided equally, right. So, 5 here and 5 there, right. So, that is an equal division, right. So, 5 here, 5 in that is 5 particles here and 5 particles there, right. So, so that is essentially so now if I ask so how many number of microstates are there here. So, if for a given n1, right. So, the total number of states are n factorial by n1 factorial times n1 factorial times capital N minus 2 n1 factorial, right. So, these are the total number of states for a given n1, right. But I can have so total W equal to W with n1 equal to 1, or n1 times W at n1 equal to 0, n1 equal to 1, and so on and so forth. So, that is just with respect to all the n1s, I am just going to take a product of all the W's, right. So, yeah, Ni, okay. So, that actually tells me that this is pi, right. So, n1 Ni equal to 0 to 5 in this case, 10 factorial by 5 factorial times 10 factorial by n1 factorial times n1 factorial by 10 minus 2 n1 factorial, right. So, where n1 it can go from 0 to 5, right. So, I have to multiply all these things to get the total number of states. Okay. So, but here in this case the number of macro states are 6, right. So, n1 equal to 0, n1 equal to 0 means, so what is my macro state? My macro state is 0 particles in n1 sorry, in this energy state, all the 10 particles in energy state 2 and 0 particles in energy state 3, or I have 1 8 1, or I have 2 6 2, and so on and so forth, or I have 3 4 3, or I have 2 6 2, or I have 1 sorry, so 2 6 2, so 4, right. So, I have to go to 4, I have 4 4 2, right. So, I have 5 0 5, right. So, I have 6 macro states, right, 6 different macro states, and each of these macro states has different micro states in them, and all the micro states add up together to give the total number of micro states. Okay. So, that is another example of a 3 level system. If you can so it is not just spin up and spin down, but I have 3 different levels in my system. Okay. So, you can also find examples of such systems in nature. Okay. Now, let us go to what is called a canonical system, right. Now, or canonical sorry, I am confusing thermodynamics nomenclature with StatMech nomenclature. Canonical ensembles. We know what an ensemble is. It is a copy of the system, keep on making the same copy of the system again and again, and the system will go to different set of microstates, right. So, those are ensembles. Okay. But what is a canonical ensemble? Canonical ensemble is equivalent to what is called a closed system. And in a closed system, you can know n is fixed. So, no exchange of particles. Between the system and surroundings. But E can exchange between the system and surroundings. There can be work done, heat, exchange between the system and surroundings. So, first of all, there is a system here, which is a closed system, which can only exchange energy with the surroundings. Okay. So, in thermodynamics you call it a closed system, in StatMech you are just calling it a canonical ensemble. Okay. Now, you also have what is called grand canonical ensemble. Okay, we are not going to talk about grand canonical ensembles here, but this is equivalent to what is called an open system, where exchange of particles and energy between system and surrounding is allowed, right. So, these are what are called open systems, right. So, I offer another course on just material growth, right. So, in ASC there we actually look at open systems, right. So, if you are growing materials, you have to really put in atoms, remove atoms, and so on and so forth. So, there is going to be mass exchange between the system and surrounding, and there so one needs to look at open systems. Okay. So, so we will just restrict our discussion to closed systems or canonical ensembles for now. Okay. So, all right. Now, couple of clarifications before I move on. One is when I say particle, right, I can mean a spin, right. So, the spin, all the number of distinct spins are particles, right. So, in my Ising model case, I can mean some sort of a dipole moment, right. So, I just mean so what is it in that system that constitutes to n? What is it that I am fixing, right. So, I am fixing the number of particles means I am fixing the number of spins when I am talking about magnetic properties. When I am talking about dielectric properties, I can fix the number of dipole moments, right. So, there are so the idea is there are all these microscopic units with certain dipole moment, and I am going to fix them, right. So, when I am going to talk about in this class, we will probably end up talking about what CV is. I am going to fix the number of energy states, right. So the particles is or number of real particles with some thermal vibrations, right. So particles is something that I loosely use to or that I generally use, right. So not loosely use to describe all these set of things, right. So depending on the problem, you can choose and pick what your particles are. Particles are spins in Ising model, particles are dipole moments when I am looking at polarization and so on and so forth. Okay. So that's the first clarification. Okay. now okay, so I have a system and I have a surrounding, right, in closed systems. Okay. Now system is okay, so I am more worried about what is happening to the system, right. And surrounding, I am going to assume that the surrounding is just a heat bath or it is a reservoir, right. So system can exchange heat with the surrounding. So this is heat is what, okay. So that is my flame, okay. So I have no idea. Okay, so I have to write it as flame, otherwise you will not understand that that is flame, right. So some sort of heat exchange between system and surrounding, but so I am going to assume that if surrounding is a reservoir, the temperature of the reservoir is fixed, right. The system would try to come to equilibrium, system will eventually equilibrate with the reservoir without really disturbing the temperature of the reservoir. Reservoir is so huge, right, it is a heat bath, right. So you can dump in anything, you can take anything from the reservoir, but nothing really changes in the reservoir, nothing meaning no temperature does not change in the reservoir. Without system will eventually equilibrate with the reservoir without really changing the temperature of the reservoir. Okay. It is a large heat bath, right. So whatever changes are happening in temperature are to the system. The reservoir has a constant temperature Tr, right. So reservoir is at a constant temperature. All right. So let us change it to a more darker color so that people do not have trouble seeing the notes. Okay, so then I am going to assume that UR is the, or not assume, I am going to define that UR is the energy, internal energy of the reservoir. I said, so the energy can exchange between system and surrounding. So UR is what total energy, this is total energy of system plus surrounding, which is the energy of the universe, right, minus UA, where A is the system, A is the system, right. UT is the energy of the universe, that is constant, right, that is conserved, that is first law of thermodynamics, energy of the universe, right. So UA and UR can sort of exchange, right. So the internal energy of the reservoir and internal energy of the so system can dump in some energy into the reservoir and take back some energy from the reservoir, right. So UR can change, right. So UR so but the temperature of the reservoir is not changing, the internal energy can change, okay, because I can just put heat without changing temperature, right. So in what are called isothermal processes, so those sort of things I can do, okay. Now sorry, so with that as the definition, okay, so what is W, so when the system has an energy of UA, right. So that means total number of states, WUA is the total number of states not in the system, in the entire universe, when the system has, or total number of microstates, when the system has an energy of UA, right. So, this is the total problem. Right. Now, total number of microstates is nothing but the number of microstates in the system itself, right. So, system has certain number of microstates, right, and the surroundings has certain number of microstates, or the reservoir has certain number of microstates, right, and both of them are sort of independent of each other. They are exchanging energy, but not really, the particles are not changing. The particles in the system remain in the system, and these particles take certain number of microstates in the system and certain other number of microstates in the surroundings, right. So, with respect to the system, the number of the states in the surrounding also changes. Okay. So, I can just write it as this, and that is equal to W A U A times W R U T minus U R. Sorry, U T minus U A. Okay. So, I want to get to the system mostly. Now, I do not worry too much about the surrounding, other than saying that the surrounding has a temperature T R, right. So, I will just use that. Right. So, I will use the temperature of the surrounding, but mostly I need to concentrate on the system, right, not really the surrounding. Okay. Now, let me simplify the problem, right. So, let me consider, I have all these eigenstates, I said, right, but so there are eigenstates in the system, there are eigenstates in the surrounding, this is surrounding, eigenstates. Okay. Now, okay, so I can define my system, right. So, first let me define the system to have only one eigenstate. Okay. So, and that eigenstate is so EI. Right. So, the system has only one eigenstate, and if I fix my number of particles in the system, if I fix n, right, if I fix my spin, that spin should exactly be in that eigenstate, right. So, there is no other possibility. So, this is my system, right. All the rest of the eigenstates are in the surroundings or in the reservoir. Okay. So, I mean, I am defining my system to be just one eigenstate, right. Then I go to the next eigenstate and define my system to be that eigenstate, right. What if the system is in that eigenstate? Then what if, sorry, again, not the system, what if all the particles are in that eigenstate, right, and so on and so forth. Okay. So, I am going to look at the probability that my system is in this eigenstate versus probability that my system is in the other eigenstate, and so on and so forth, right. So, like that I am going to combine a set of eigenstates and understand this problem. Okay. But so for now, play along with me and let us divide my system. System and surrounding is sort of a free definition. So, I'm just going to say, okay, so I just consider this eigenstate to be my system and the rest to be the surroundings, right. Okay. So, which means that all my particles are in this eigenstate, right. So, I am just going to define, I am just going to look at all those scenarios where all the particles are in this eigenstate. Okay. All right. So, then so W A E I, so the number of eigenstates are in the system, right. So, E I meaning the eigenstate I is just 1, right. So, there is just one eigenstate. Okay. So, the total number of eigenstates then in the, this is total number of eigenstates in system plus surrounding is nothing but W A E I, which is 1 times W of the reservoir, and the reservoir has an energy of E total minus E I, right. Or so E we used U T, right. So, U total minus U I. Okay. All right. So, essentially the total number of states are just defined by the total number of states in the reservoir, U T minus E I. Okay. All right. So, now I can actually define the the temperature of the bath of the heat bath, right. So that's the quantity of interest for me, right. So in fact, so from StatMech, temperature is a derived quantity. Temperature is not something which is assumed. Like in thermodynamics, you assume that temperature is, what is temperature? Temperature is so I know what temperature is. Temperature is something very fundamental. It's like mass of a material, right. So it's something very fundamental. But from the point of view of StatMech, what is more fundamental are the entropies, right. So the internal energies of the system and so on and so forth. And so I can actually define temperature as dou S by dou U, right. So this is 1 by T. Okay. So this is the definition, StatMech definition of temperature. Okay. So now I ask the question, what is the temperature of the reservoir? I know the number of so once it equilibrates, the reservoir temperature is the same as the system temperature. So what is the temperature of the bath? That's the question, right. So the temperature of the bath is nothing but dou SR by dou UR, right. So that is 1 by T reservoir, or 1 by T of the bath. Okay. Now so what is SR? SR is nothing but KB times WR, right. So WR UT minus EI. Okay. And so UR is just UT minus EI, again that is UR. Okay. So essentially from the statistical mechanics definition of temperature, what we get is so 1 by KBT, 1 by K, so here I am just writing it as KB, KB is the Boltzmann constant, is equal to dou ln WR by dou UR. Sorry, there is a ln here, right, and that is at a constant volume, but okay, so that's, we will not pay too much attention to that now. Okay. So or in other words, WR is some sort of an integration constant, gamma, you can see here. So this is a differential equation, right. So if I just look at what WR is some sort of a gamma times exponential of UR. Now UR is the energy of the reservoir, right, divided by KBT. So finally we got this exponential of 1 by KT sort of thing, right. So the number of states, right, is some integration constant gamma times exponential UR by KBT. Okay. All right. So then WEI we said is nothing but WR UT minus EI. Okay. And that would be equal to gamma times, we know what WR is now, exponential of UT minus EI, that is UR by KBT, right. So the total number of states, right, system plus surrounding, is actually now expressed in terms of the temperature of the reservoir, right. Now okay, so here I am actually assuming my system is just EI, right. So if EI is my system and rest of it is surroundings, the total number of states under this so by defining this sort of a micro system and rest of it being the reservoir is this. Okay. However, so we have to, what are the total, so I can have my system in EI, I can have my system in so EIs can be different, right. So I can then go to an eigenstate EJ, I can go to an eigenstate EK, and so on and so forth. So the n total, or so the total W of my system now, right. So now I'm going from these micro systems of just defining EI, EJ, EK to so all these energy levels exist in one system, right. So the total number of n total of microstates will just be so a summation of all these things, which is just gamma exponential of UT by KBT. However, there is going to be a sigma here, exponential minus EI by kBt, where EI and I is summed over all the states. So, 1 to some n number of states that I have, all the eigenstates are summed over. Okay. Okay, so this is the total or n total, right. So this is the total number of microstates. I am just going to write it as script n or script w, right. So because we are using w, so this is the total number of microstates in the system. Total number of microstates, right. So now I have calculated it by looking at different by defining different microsystems and looking at their reservoirs. Okay, so this is the thing that I'll get. Okay, now this is the total number of microstates altogether, right. So this is in the universe. How many microstates are there? This is the total number of microstates. If my system exists in eigenstate EI, the total number of microstates are gamma exponential ut by kBt exponential minus EI by kBt. If it exists in EJ, then total number of microstates are EJ by kBt and so on and so forth. So I add up everything, right. So and I get this expression. Okay. Now I ask the question then, what is the so each of these microstates is equally probable. My system can either exist in EI or EJ or so whatever be the microstate that I define, right. So my system can equally probably exist in all these microstates. Okay. So here I have made my life simple by saying either system exists in EI or EJ or EK and so on and so forth, right. Okay. So then what is the probability that my particles or so my particle, right. So if I have one particle system, let us say, so this particle exists in an energy state of EI. Okay. So I think that will be easier to understand. Let us just assume that I have a one particle system, right. So if when I have a one particle system, what is the probability that this particle exists in an energy state EI, right. So that is given as the probability, right. And this probability here I will use the fundamental theorem of StatMech, where the probability that my particle exists in an energy state I, that is a microstate for the particle, is the same as the probability that my system will exist in an energy state J and so on and so forth. So it will just become 1, which is so it will just become W of EI divided by capital W, the script W, right. So the number of states that exist when my particle is in an energy state EI, right, divided by the total number of microstates. Okay. And all these are actually coming from the WEI, are actually coming from the surroundings. The system still has only one microstate, right. The particle is in EI, right. But the surroundings are sort of reorganizing themselves so that so you have so you have all the WEI number of microstates. That is because the system can give away its energy to the surroundings, right. Okay, so what is that? That is just exponential of minus EI by kBt divided by times gamma times exponential e power ut by kBt divided by the same thing exponential ut by kBt, the integration factor, times sigma exponential minus EI by kBt. Okay. So this gamma goes away and what I have is the probability that my particle has an energy EI, right. Now I do not need to worry too much about the microstates and macrostates and all these things, is just minus EI by kBt divided by sigma exponential minus EI by kBt. Okay. Now the probability that my particle has an energy I versus the probability that my particle has an energy J is different, right, because the number of microstates in the system are different. This is a closed system. This is so this is, if it were an open system, right. So the probability that the system has so because this is a closed system, right. So not all microstates of the system are equally probable, right. So this is one microstate of the system, but it is weighted by its energy, right. So, the E by kBT sort of weighs it in a closed system. Okay. So, this is the probability that the system can exist in a microstate in an energy eigenstate of Ei. Okay. Now, look at the denominator. The denominator, which I am going to define it as Z sigma exponential minus Ei by kBT, right. Now, I equal to 1 to all the number of, so I, so it is a summation over I, all the energy states, right. So, this is what is called a partition function. Okay. Now, okay, so I have, so what is this partition function really saying, right. So, this partition function, right. So, if you look at it carefully, this partition function has probabilities, all probabilities are added up, right. So, so it has information about energies of all the states weighted by the temperature of the reservoir, right. So, partition function in some sense has the entire microscopic picture of the all the microstates of the system, and also the surroundings, and the surroundings peak in just by this kBT, surroundings come as kBT 1 by kBT, right. So, we will see how partition function is very useful, but from a statistical mechanics point of view, partition function is a summation of E power Ei by kBT, right. So, the system can exist in different energy states. Okay. So, now the total energy of the system, right. So, of the system, right, it can keep changing, it can be Ei, it can be Ej, it can be K, and so on and so forth, right. Each of them I am going to define it as so what is the probability that my system has an energy Ei, right. So, by Pi, right. So far in my particle picture I sort of said what is the probability that my particle has an energy Ei, okay. But now I can sort of generalize this and then say, okay, so my system itself can have an energy Ei, then my surrounding will have an energy Ut minus Ei, right. So, what is the probability that my system has an energy Ei, that is given as Pi, right. So, I can define this, I can look at this probability function, this probability as the probability that my system, now I have come back to system, I do not care about surrounding anymore, all the information about surrounding has come through this T, right. So, the temperature of the heat bath, okay, that my system exists or has an energy Ei, right. System's energy can keep changing, it can be Ei, Ej, Ek, whatever, right. So, system's energy can keep changing, right. So, now this has so all possible energies of the system, right. So, this knows everything about if system has Ei, the probability is E power minus Ei by kBT, right. If system has an energy Ej, it is Ej by kBT, and so on and so forth. So, the partition function has all possible combinations of where my system can exist, what is the energy state of my system, okay. So, given that partition function has all the microscopic knowledge about my system, right. So, let us keep it that way. So, partition function has all the microscopic knowledge about my system, also the surroundings, so assuming that system is in a heat bath, the surroundings come as a kBT factor, right. This is the Boltzmann factor, okay. So, that is how I understand the partition function, all right. Now, let us relate, so Z turns out to be your connection between microscopic picture, where I do statistical mechanics, and a thermodynamic picture. Right, where I look at thermodynamic potentials, where I look at the properties as double derivatives of potentials and so on and so forth. It turns out that the Z is very crucial. Z or the partition function is something which is very crucial. Okay. Okay. So, now based on the partition function, so you can also show for yourself that S, right. So, S is nothing but minus k sigma pi k pi, sorry, pi ln pi, right. So, where pi is the probability that the system has an energy ei, right. Okay, so let me write it down. Pi is the probability that the system has an energy ei. Okay. So, then the total entropy of the system will become this, right. So, now the entropy, so there is a temperature that comes in at every pi, right. So, and pi is actually, because pi is actually equal to e power minus ei by kBt divided by partition function z, right. So, this is something very important that comes out of StatMech, right. So, energy of the system. Now, this energy of the system can, it is some sort of an internal energy of the system, right. So, that can keep changing because the system is exchanging energy with the surroundings, right. So, all right. Okay. So, with that, so let us look at what is S, right. So, S is actually minus kb sigma pi ln pi. Okay. Now, what is ln pi? We have this, so I can just write ln pi as ln exponential of minus ei by kBt, okay, minus ln z, right. So, that is so here if I take logarithm on both these sides, I get this expression, right. So, that is what, that is just minus ei by kBt minus ln z. Okay. So, that is yeah. So, that is, so I have entropy which is a thermodynamic quantity. Now, I am trying to relate it to partition function. Okay. So, and okay. So, let us see what this is. Yes. So, S, let us go back to S. So, ln pi, I have an expression for ln pi, let us write that. So, but S is minus kb sigma pi ln pi, right. So, this is something that you can see for yourself, so this just comes from S equal to k ln omega, k ln w, right. And then, sort of if I have all the I states with different probabilities, it turns out that S can be expressed as this. Okay. So, this is something that we did for microcanonical ensembles, but the same thing is valid for also canonical ensembles. Okay. Then, so what is that actually? So, I have an expression for ln pi. Ln pi is nothing but ei by kBt, okay, minus, again there is a sigma pi ln z. Okay, so if there is a minus here, there will be a plus here, right. Okay, so now that is kb and kb is outside, sigma pi ei, right, by, so because the summation is over I by kBt, okay, plus kb sigma pi and summation is over I ln z, right, and sigma pi is just 1 and sigma pi ei is the total energy, internal energy of the system, right. So, that is that I am going to write it as U bar, right. So, this is the internal energy of the system, US, right. So, something UA, we took it as UA. Okay. So, what is so S equal to K U by T, right. So, the kb cancels out, u by t plus kb ln z, right. Or in other words, I have u minus T s, where T is the temperature of the reservoir, S is the entropy of the system, is just kb T ln z, right. Now, what is u minus T s? U minus T s is one of the potentials that we defined, right. In fact, we defined our potential that we defined as u minus T s minus so if I have other forms of energy such as the electrical energy, I have E d minus x x, right. So, this is what I defined as my phi 2, right. But so if I do not have electrical energy and stress and strain energies, then so u minus T s is something which is called Helmholtz free energy. Okay. And you can see that Helmholtz free energy F is actually related to temperature, right. It will be related to the volume of the system, right. But if I also include this and call this the Helmholtz free energy, right. So, then F will be, or phi 2, I said it is phi 2, but so I can also call this as the Helmholtz free energy. That will be a function of temperature, the electric field, the stress in the material, right. That's what is the Helmholtz free energy. Okay. So, it is a particular thermodynamic potential, right. So, if I look at what dF is, dF will be minus S dt, so in this case where I just have PV sort of work, so minus PdV, right. So, if I change V, if I change T, I change F, that is what this means. Okay. So, the potential where the control variables are T and V is the Helmholtz free energy, right. So, similar to our phi 2, or so let us call it F 2, right. F 2 will have minus S dt minus d dE minus x dx, right. So, F 2 or phi 2, right. So, dF 2. Okay. Anyway, so this is essentially, so so u minus Ts, given that the only form of energy, only form of work I have is the PV work, is what is called the Helmholtz free energy. F, right. So, according to StatMech, right. So, F, which is my thermodynamic potential, is so this is actually F, u minus Ts is F, right. So, there should be a minus coming up. So, maybe I u minus Ts, yeah. So, when this goes this side, there will be a minus, right. So, F equal to minus kBT ln Z, right. Now, what did we tell about Z? Z has all the microscopic properties, microscopic information about the system. And what is F? F is a thermodynamic potential. Right. So, what is, but this thermodynamic potential is exactly the same as some sort of a logarithm of Z, right. So, kBT logarithm of Z, right. So, Z, or the partition function, is what relates the microscopic picture or the statistical mechanics picture to the thermodynamics or thermodynamic potentials. Once I know thermodynamic potential, thermodynamics tends to be very mathematical, right. So, with the thermodynamic potentials or thermodynamics. So, I can do all the thermodynamic calculations if I know the potentials. such as Helmholtz free energy, the phi 1, phi 2, all the thermodynamic potentials that we looked at, right. So, here is my connection from stat mech to thermodynamics, right. So, this is stat mech and this is thermo, but I have my Z which has all the information, it has sniffed, it is my spy. Thermodynamics has sent this spy, right. So, now the story becomes more clear, right. So, this is like a movie where so the guy is working with the mafia, but then later on that the police had sent this guy, right. So, to understand the workings of mafia. Okay. So, all the microscopic picture is in Z sort of knows everything about the system, the microscope, so what are the various energy states, what is the probability that the system is spending in each of these energy states, what are the micro states, what are the macro states, everything Z knows, right, or Z has it in it, right. And so later that in fact kBT ln Z or minus kBT ln Z is nothing but my thermodynamic potential that I have been using all this while, the F, right. So, thermodynamics has sent its spy Z to spy over the entire microscopic system, and that is how you get the connection of what is the microscopic picture with the macroscopic world, that is thermodynamics. Okay. So, let us stop here for now, and then in the next class we will actually look at so right now we have the framework, since we have already defined what F is. From F we will look at what the properties are, because properties are just curvatures of thermodynamic potentials, and how would they relate to what does it mean that the properties are curvatures of these potentials, because now we have a microscopic picture in the form of Z, right. So, so this double differentials dou square F by dou T square, right. So, that is CV, right. So, what does it mean in terms of the microscopic picture, right. So, what do these properties actually mean in terms of the microscopic picture. So, let us come back to that in the next class. Okay. So, with that I will end this class here. Thank you very much.